Hello class and welcome to the Group 8 presentation of Sapphire, a customizable and extensible deployment of mobile cloud applications. My name is Michael Machovis. What is Sapphire? Sapphire is a new programming system for deploying mobile cloud applications. The motivation behind it, that modern applications basically were difficult to implement in distributed systems. Programmers had to combine code to cross smartphones, tablets, cloud services, connected all by a varying wide area networks like Wi-Fi, 3G, etc. And they need to be able to have a solution for complex distributed tasks like fault tolerance, caching, and scalability. Now there were three main difficulties. The first is that there may be many distributed deployment decisions made that depend on application requirements. These can create bad performance versus function trade-offs. The second is that there is a dependency between application and deployment. So mixing application logic with deployment decisions can create a difficult environment to implement, debug, maintain, and eventually evolve. And the last difficulty is evolution itself, but evolution of devices, networks, systems, etc. All this requires some sort of flexible system in order to be able to adapt. So the three main purposes outlined by the paper. One was the separation of application logic from deployment code, which we just said was one of the main difficulties of performing these type of tasks. Two is to create a distributed program spanning devices in the cloud. And three was to allow programmers to easily choose and change the application deployment. So that's the flexibility that I had just mentioned is necessary and required and desired most of all. So the architecture is broken into three parts. There's the Sapphire application, the deployment management layer, and the deployment kernel. The separation between the deployment kernel and the deployment managers provides significant flexibility and extensibility within the Sapphire platform. So that's one of the main purposes, is to offer that type of flexibility. And also by separating application logic from deployment decisions, the application complexity is reduced and the deployment can now be easily changed and manipulated. And now we can take a closer look at each of these individual parts. So the first is the Sapphire application. This piece encompasses all client and server-side application logic, and it is made up of Sapphire objects. The application model is object-based, and it can be integrated with any object-oriented language, but this particular paper and their test implementation, they only use Java as their object-oriented language. The logic must be built as a single object-oriented program, and then the application will then be broken down into declaration sets of objects as these Sapphire objects, which the deployment managers can be assigned to these objects for better management. So the deployment management layer. So this consists of the deployment managers. These can customize and control behavior of the individual Sapphire objects in the distributed mobile cloud environment, so the objects that they are in fact assigned to. There is direct support for the deployment managers through the deployment API that we will talk about a little later. Uh, and this API is designed for developers who will develop more complex applications. They can accomplish complex distributed tasks by the deployment managers telling the deployment kernel what to do, because the deployment kernel kind of does all the bulk heavy lifting. And the deployment kernel, this is a runtime system. Its main goal is to create an integrated execution platform across device and server. So it has four main functions. The first is management and location tracking of Sapphire objects. Second is location transparent inter-object communication. The third is low-level replica support. And finally, services to simplify the writing and execution. So the kernel is made up of servers that run on back-end computing devices and a centralized object tracking system, or OTS. So the object tracking system is similar to some that are already in existence, like Chubby, Zookeeper, and Tango. And they track the Sapphire objects over the kernel servers. These servers hold multiple objects and act as event servers for them, as well as hosting the deployment managers that are assigned to those objects. And in any case, if the server ever becomes overloaded, it will contact another server to host an object, move that object from its current location to the new server, and update its location inside of the OTS for tracking. So the Deployment Manager API, which I had previously mentioned, was designed primarily to have minimal interface. That was its primary goal, but at the same time support a great deal for programmers. So it is a single deployment manager, extends the functionality of the deployment kernel to meet the Sapphire object requirements. It consists of an instance manager, which is co-located with the Sapphire object, proxy, which is co-located with remote references to the Sapphire object, and a coordinator, which is co-located with fault tolerance object tracking service. So there is, this is a library of the deployment managers. So these go from primitives, caching, serializability, checkpoint, replication, mobility, and scalability. This gives the ability to incorporate many different features for as far as managing the Sapphire objects. They provide usefulness for applications as well as flexibility and ease inside of the frameworks. This paper outlines 4 specific examples of the different usages one can get out of these types of deployment managers. The first is code offloading, which is useful for compute-intensive applications. Under the mobility category on the library of deployment managers slide that we just saw, you can see that there are 2 types of code offloading deployment managers. The first is code offloading, which supports transparent object migration. And the second is explicit code offloading, which allows applications to decide when to move computation. There is more control using the explicit code offloading because code offloading is automated, but it is also less transparent because the Sapphire object interacts with the deployment manager. The next is peer-to-peer. So the peer-to-peer supports direct sharing of Sapphire objects across client mobile devices without needing the cloud. Um, they dynamically place replicas on nodes containing reference to the Sapphire object, and the replicas will never exceed its specified maximum. The next is replication. So the library has three different replication deployment managers that replicate Sapphire objects across several servers. These model the Sapphire object as a replicated state machine, which execute operations on master replica. The replicated state machine uses a coordinator to instantiate the number of replicas along with other information regarding membership to the replica group. And the final one is scalability. So there are three DMs in this category that include both stateless and stateful scalability. The first is load balanced front end deployment manager, which provides simple load balancing among a set number of replicas, only supporting Sapphire objects that are stateless. It can, however, access state in other Sapphire objects or on a disk. The scale-up front-end deployment manager extends the load balance front-end deployment manager with auto scale-up. It monitors the latency of requests and creates new replicas when the load and latency increase. And the last deployment manager in this category is the load balanced master slave, which provides scalability for read-heavy workloads. This DM dynamically allocates a number of read-only replicas that receive updates from the master replica. So now we can take a look at the deployment manager structure. So there are this consists of three component types: the proxy, the instant manager, and the coordinator. A deployment manager is built by defining three object classes, one for each type. The deployment kernel creates a distributed execution environment, and when it instantiates a Sapphire object with an attached deployment manager, it also instantiates the deployment manager and its components. So the deployment kernel also allows for transparent RPC between deployment manager components. And now the deployment manager components. Each component of the deployment manager is responsible for a particular set of distributed tasks. So proxies are responsible for caller-side tasks like routing method calls. The instance managers are responsible for callee-side tasks like keeping replicas of the Sapphire object synchronized. And finally, the coordinator is responsible for centralized tasks such as failure handling. All three components are optional. So in other words, a deployment manager can define one or more of these components, and the deployment kernel will instantiate only those components that are defined. And this is a deployment manager example. So in this example, you can see the deployment of deployment manager components for a Sapphire object A. As seen here, the deployment kernel can instantiate multiple proxies and instant managers, but there can only be one coordinator, so that's pretty important. And the DKFT is set of fault tolerance DK nodes. Now we're moving on to the implementation. So here is the prototype that was implemented for the paper. So the prototype here was built using Java, as I had said before, specifically to accommodate Android devices. So it consists of nearly 13,000 lines of Java, which include about 11,000 lines of Apache Harmony RMI code that must port to the Dalvik. You can see from the figure here that the Sapphire can be run in a cluster using Sun's Java 1.6.0 38 JVM, but tablets and phones are running on Sapphire running Sapphire on Android 4.2 Dalvik VM. So Java RMI only provides point-to-point communication and only supports calls to Java objects. Therefore, it can only be used for low-level communication between the deployment kernel servers and the OTS. A compiler creates stubs for the Sapphire objects, and the deployment manager, instant managers, and coordinators. Having stubs for each Sapphire object allows deployment kernel server to route RPCs and invoke the deployment manager components. And the stubs are created as Java classes that extend the class of the target object. Now, moving on to evaluation, there were 3 objects to be considered in the design and implementation of several Sapphire applications. The first is deployment ease. It should be easy to develop mobile cloud applications, either from scratch or by porting non-distributed mobile device applications to Sapphire. And it should be possible to write application code without explicitly addressing distribution management. The second is deployment flexibility. The programmer should be able to choose from alternative distribution management schemes and change deployment decisions without having to rewrite the entire application code. And the last is management code generality. So it should be possible to build generic distribution management components that can be used widely both within an application and across different applications. Moving on to the experimentation or the actual implementation defined here in the paper. So there were the performance of 5 categories were tested. The paper only outlines 4 of those 5. So it outlines caching, peer-to-peer, code offloading, and scalability. For caching, 2 deployment managers were tested, release caching and consistent caching, both of which improved latency of reads from 6 milliseconds to 0.5 milliseconds and from between 7 and 13 milliseconds to down to about 2 to 3 milliseconds. The write cost, however, to keep caches and clouds synchronized increased significantly from 29 milliseconds to about 77 milliseconds. For code offloading, compute-intensive applications were tested using code offloading deployment managers on 2 devices, the Nexus 7 tablet and the Galaxy S smartphone. So the trade-offs here varied widely between the 2, primarily based on differences in CPU speed, wireless, and cellular network card performance. The varying results really show the importance of flexibility in this type of situation, and that there's a need for it to be the ability to easily change, to be able to adapt. Scalability, they tested the load-balanced front-end deployment manager, and it was used to scale a stateless Sapphire object under a heavy load. This creates a given number of replicas and assigns clients to the replicas in a round-robin fashion. And lastly, for peer-to-peer, they measured 3 deployments for the game Sapphire object in a multiplayer game. So the first was without a deployment manager, which deploys a Sapphire object on the server where it was created. The second used Keep on Device Deployment Manager, which dynamically moved game object to device that accessed it. And the third used Consensus RSM P2P Deployment Manager, which created synchronized replicas of the game Sapphire object on callers' devices. And now we have some graphs of the results from here. So here we have displayed the results from the scalability test that they had run. This graph demonstrates 3 different types: a 1-node, a 2-node, and a 3-node. And you can see from the figure that the throughput of the Sapphire object serving null when the RPCs, when the deployment manager creates up to 3 replicas, and that the throughput scaled pretty linearly with the number of replicas until the network pretty much saturated just at about 250,000 requests per second. And moving on to peer-to-peer results. So this graph displays the 3 different tests: the node deployment manager, the coupon device, and the consensus RSM P2P. So for node deployment manager, you can see that host and guest, the latency for both are pretty even but kind of high. Both pass about the middle ground of this graph. Whereas the keep on device DM, the read and write latencies of the host are extremely low, so low to the point that they actually barely make the graph. However, they are somewhat higher for the other player, even higher so than not running a deployment manager at all. Now, for the consensus, you can see that both read latencies were much lower on both devices. Now, whereas the write latencies are kind of high. So I think one of the big takeaways from this is that this kind of demonstrates the need for flexibility, and that the ability to choose and change the type of deployment is particularly important. Um, as this graph shows, there can be quite a difference in just the latency and the type of deployment that is chosen. So to be able to change on command without having to rewrite an entire application is quite a successful endeavor, and quite useful one at that. So in conclusion, 3 takeaways from this is that modern applications, the implementation is difficult for distributed deployment tasks. And again, that was due to things like the decisions that had to be made, the evolution of devices, and the fact that these need to be cross smartphones, tablets, cloud services, and also connected by different type of networks. And so Sapphire is a new programming system for deploying these types of mobile cloud applications in a way that is flexible, and that deployment managers can make it easy to choose and change and build deployment that has and encompasses that flexibility and that ease into the framework.